Hello everyone, this is Yogesh Muramkar. In this video, we are going to discuss about transformer architecture in detail with very simple explanation using the concepts like self-attention, multi-head attention, positional encoding and layer normalization. So self-attention, multi-head attention, okay, positional encoding and layer normalization. And by chance, if someone is not aware about any of these concepts, please don't worry. I'll try to give you basic understanding of these concepts whenever required. And if someone wants to understand all these concepts in detail, I'll create separate videos for it. Okay? So also before starting the explanation, let me tell you that the link for notes and all the diagrams have been provided in the description of this video. Whenever I say notes and all the diagrams, may see everyone, I'll be using all these things. I'll be explaining you the concept of transformer architecture with a very simple explanation. Everyone will be able to understand it. Okay, so all these things are already shared. You can click on the link provided in the description and you can download all this stuff. So that if you want to revise these things, you can easily revise and try to understand the concept properly. Okay. So I have broken down this particular transformer architecture into two parts. In this video, we will focus only on encoder part of the architecture, as it is mentioned here. In the next video, we will focus on the decoder architecture. Okay, so what is encoder, what is decoder? We will talk about it. The main goal of this video is to understand the encoder architecture well. And I'll be using these handwritten diagrams for the entire explanation, whatever I have shown you just now. So let me explain the journey of understanding transformer encoder architecture from the very familiar diagram which you are able to see here. Okay, I hope so. Everyone is able to see this properly. Starting with the inputs, input embedding on this side, and here you can see output shifted right, output embedding and so on. Okay, this is the very familiar diagram. By chance, if someone has come across something like transformer architecture, definitely they must have come across this particular diagram. So see everyone, this diagram represents the entire transformer architecture. Both encoder and decoder are inside this. But the problem is that this diagram is very complex. If someone sees this diagram for the first time, they will feel a little confused and some things will not be understood by them. But if I try to simplify this diagram a little, then things become easy. Let me ask you, do you at least see or do you at least understand that there are two parts in this diagram? One part is here. You can see everyone. This one. First part of the diagram. Okay, on the left side, and another part is here, this one. See, I am highlighting it. Okay, then we can say clearly this part is our encoder. On the left side you see this one, everyone, this is our encoder part, and this part is our decoder. Okay, so I can show you this particular diagram in a very simplified way like this. You see here. So whenever I say transformer architecture basically will have two blocks, encoder and decoder. So in a diagram which I shown it to you here, you can see this is the encoder part and this is the decoder part. Okay. One more thing everyone you can notice, next to encoder here, you see this NX is written, right? Next to the encoder block as well as decoder block as well. You see NX here and NX here, right? Or N written here. and here as well. This n means what? This n means that there is not just one encoder block, but there are multiple such blocks. Not only one encoder block, but there are multiple such blocks. Similarly, there is not just one decoder block, there are multiple such decoder blocks. If you read the original Transformer paper, you might be knowing the name of the original Transformer paper is what? Attention is all you need. Okay, maybe most of you might have come across, definitely. This is a paper written by 8 people from Google Brains. Okay, so if you read the original Transformer paper titled Attention is all you need, you will find that they basically used 6 blocks for the encoder. How many? 6 blocks. And 6 blocks for the decoder. So if I want to show the next thing, the architecture basically looks like this one. 6 encoder blocks and 6 decoder blocks. See, 6 is not a magical number. They achieved it through experimentation. And the number 6 basically gave them best results. That's the only reason. Otherwise, there is no specific reason why 6 encoder blocks and why 6 decoder blocks. Okay. Obviously, the question might have arisen that why 6? So I've told you, right? It's all through the experimentation. Okay. Now the next question might be like, are all these blocks identical? Whenever I say 6 encoder blocks, are all these blocks identical? The answer is yes. All these blocks are completely identical, meaning their internal architecture is exactly same. I can say copy paste. This means if you understand one block, you automatically understand other 5 blocks as well. Okay. So obviously our focus is now to understand single encoder block. What goes inside one single encoder block, that is what we will try to understand. Okay. So now moving forward, everyone, as I've told you, this is the transformer architecture. Out of this, we will try to focus on the entire encoder part. In the next video, we will try to discuss about the decoder part. So the architecture in a simplified way looks like this. Inside one encoder, there are 6 encoders. So it looks like this. And now we will go inside one encoder, everyone. Okay. We will go inside one encoder, and that one encoder basically looks like this. Okay. So when we zoom into a single encoder block, we find it contains 2 smaller blocks. Okay. This basically contains 2 smaller blocks. First is a self-attention block. Second is a feed-forward neural network, as you can see clearly here in this particular diagram. Next, let me explain how data flows through complete encoder. Okay, let's try to discuss about that with a very simple example. Your sentence enters the first encoder block. See, as I've told you, there are 6 encoders, 6 decoders. So your sentence enters the first encoder block. The first encoder block looks something like this. See everyone, as I've shown you, okay, something like this. And if I want to show you what exactly happens when I say feed forward neural network and self-attention, so it looks like this. The first encoder block, everyone, looks like this. From where I got it, so you see here, in this case, multi-layer attention, add and norm, feed forward, add and norm. Exactly same thing is shown here. Multi-layer attention, add and norm, feed forward, add and norm. That is what I am trying to show you. And like this, how many are there? 6 encoder blocks are there. So the diagram basically becomes something like this one. You can see, as I have told you, your sentence enters the first encoder block. This is the first encoder block. And the first encoder blocks look like this. It looks like this. The output from the first encoder block goes to the second encoder block. Even though I did not draw it here, but you can imagine it is exactly same. I've told you, right? So the output from the first encoder block goes to second encoder block. The second encoder block is identically the same. Then processing happens inside second encoder block as well. The output from this second encoder block goes to the third one. The output from the third goes to the fourth, and so on till the sixth encoder block. Finally, our sixth encoder block output goes towards decoder. Okay, as you can see here. So what exactly is 3 cross 512, how it is achieved, we'll talk about it. Fine, but I hope so you got an overview. Whenever I say some input is passed to the encoder, what exactly happens. So this is like high level overview, I can say. Fine. Finally, as I've told you, our sixth encoder block output goes to decoder. And one more thing, everyone, before the input enters the first encoder, this input, before it enters first encoder or first encoder block, there are 3 important operations which are performed on the sentence. Let me take an example, everyone, and explain each and every step to you. Okay, so see here, let's say before input enters the encoder block, what exactly happens, let's try to see this. Okay, and I've told you already that there are 6 encoder blocks. So for example, everyone, let's say I have a sentence, I have an example like this: I am Yogesh. Okay, the first operation which comes into picture is tokenization. You can see here, tokenizer. This means the tokenizer will break our sentence into words. Okay, tokenization means you break down a given sentence into tokens. And tokens could be a single word, 2 words, 3 words. It depends on the tokenization approach. For now, we are doing word level tokenization. This means the tokenizer will break our sentence into words. Let's say first token is I, another token is am, and next token is Yogesh. The second operation is very important. This one. This is also called as text vectorization. This means your encoder or transformer cannot process words. Obviously, no machine can process words, right? You must somehow convert them into numbers. The technique we use for text vectorization is called embedding. The technique we use for vectorization, for text vectorization, is called embedding. What we do is that we take every word and put it in this embedding layer. And this embedding layer will generate a vector of every word. In our case, it will be 512 dimension vector. Okay, that's why I have written here 512 dimension vector. It's like this: 1, 2, 3, 4, and so on. 512 dimension vector. Fine. This means for the word I, or the token I, we get a 512 dimensional vector representation. Similarly, for words am and Yogesh, we get 512 dimensional vector representation. But the problem is, we don't have any information about the order of words. Which word comes first? Which word comes later? We don't know that. And guess what? This is very, very important. Obviously, you must always know which words in your sentence come first and which come later. So to add this positional information, we use a technique called as positional encoding. basically this icon you can see everyone, this is for positional encoding. Okay, if someone has come across the transformer architecture shown in the attention is all you need paper, you must have seen, right? They also have used the same notation. So everyone, to add positional information, we use a technique called as positional encoding. For each position, like position number 1, it will generate a 512 dimensional vector. Similarly, for position number 2, it will also generate 512 dimensional vector, and similarly for position number 3. Now, those 512 dimensional vectors are P1, P2, P3. Okay, and even E2, E3 are nothing but what? These are the 512 dimensional embedding vectors for I and M and Yogesh respectively. Now we have to add our embedding vectors with their positional vectors. So basically we add these two vectors E1 and P1. We add these two vectors E2 and P2, and then E3 and P3. You can see this addition operation. So after all these addition operations are even, we get 3 new vectors. As you can see, I mentioned here x1, x2, x3. x1 is what? It's embedding of I. It's embedding of I. Right? This is for I, this is for M, and this is for Yogesh. These are the embeddings. So x1 is what? x1 equal to embedding of I plus positional encoding of position 1. x2 is what? Embedding of M plus positional encoding of position 2. And x3 is what? Embedding of Yogesh plus positional encoding of position 3. This is how we got x1, x2, x3. Now these 3 vectors x1, x2, x3 enter the first encoder block. It means what even? It means the previous diagram which I shown you, this one. This x1, x2, x3 will enter this block, because now everything related to input operations is done. Now that x1, x2, x3 will enter first encoder block. That is this one. I hope so you are able to see that. It means what? It means everyone, in our architecture, where are we right now? If you want to understand that, so I'll just point it out. So see everyone, we are here. Okay, we are here. Fine. So they encounter this x1, x2, x3. As I've told you, they enter the first encoder block, and first they encounter the multi-head attention block. You see, multi-head attention. The first thing which they will encounter, x1, x2, x3 will encounter is multi-head attention. So whatever we got here, this x1, x2, x3, right, they will encounter multi-head attention. Or here also, in this diagram also I can show you. You see, input will encounter multi-head attention. Please try to understand. I am just trying to break these in small parts so that it will be easy for you to understand. Fine. Now, self-attention, that is this multi-head attention even. Multi-head attention is like multiple self-attentions. Okay, so that's why I'm saying self-attention is applied because your embedding vector has a problem. This multi-head attention is multiple self-attentions. Now why this self-attention is applied even? Why it is applied? So that's what I'm trying to tell you. Self-attention is applied because your embedding vector has a problem. This x1, x2, x3, it has a problem. The problem is that the same word has same embedding everywhere. Please try to understand. The same word has same embedding everywhere. For example, let's say a very common example even, which you will find out everywhere. Let's say I have a sentence like this. I went to bank. Okay, this is the first sentence. Another sentence is I sat on the river bank. This is another sentence. Now here everyone, in this case, both these sentences, sentence 1 and sentence 2, they use the word bank, but with completely different meanings, right? Yet the embedding will be exactly same for both. Embedding is nothing but what? Embedding is nothing but representing these words in terms of vector, numbers. So embedding will be same for them because bank and bank word is same. So self-attention solve this problem, because if you see here in this case, I went to the bank. Bank is basically used in the context of financial institution. And here in this case, I sat on the river bank. Bank word is used in some different context, like river bank they are talking about, right? So obviously everyone, their embedding should not be same. So self-attention solves this problem. As soon as you apply self-attention, you notice that the embedding of bank in the first sentence and the embedding of bank in the second sentence changes. It starts considering surrounding words contextually. It becomes contextually aware. Okay, and what is even better than self-attention? It is multi-head attention. Because in multi-head attention, everyone, in multi-head attention, you bring multiple self-attention modules and get opinions from all of them. It's like one opinion is good, two opinions are better, and more opinions means you have more diversity. So without going into the details of what is happening inside this block, I will directly give you the output, or I'll directly show you the output. Right? This block I am talking about. So when you send the first vector through multi-head attention, that is this x1, through multi-head attention, you get another vector z1, which is again a 512 dimensions. Okay, this is again 512 dimensions. But this z1 will consider surrounding words contextually, that is z2, z3. Similarly, when you send x2, this is basically vector for m, embedding vector for m. You get, when you send x2, you get z2, right? And when you send x3, you get z3. So all of them, they are basically 512 dimension vectors. Now here is something very good that is happening. We use residual connections. Everyone, this is called as residual connection or skip connection. Okay, residual connection or skip connection. In the original diagram as well, you can see here. See, this is what I am talking about. This line is called as residual connection or skip connection. Okay, this one. Notice here where it says add and norm. You see, add, that is actually for this residual connection, everyone. This add is actually for residual connection. What happens is when you send your x vectors, these x vectors, x1, x2, x3, when you send these x vectors, that is x1, x2, x3, one path goes into multi-head attention. You see? Okay, you see here? This goes into multi-head attention. x1, x2, x3 will come from here and it will go into multi-head attention. Right? That is nothing but this one. Okay, as we have three words, that's why it is like this. So one path goes inside multi-head attention, but another path does what? It bypasses the multi-head attention and goes ahead. See, you see again, it bypasses this multi-head attention and you can see it goes here. Right? It goes ahead, or here you can see again same thing as I've told you. This one, it bypasses this multi-head attention and it goes ahead. So we have two sets of vectors at this point. You can see, because of this residual connection, it has bypassed the multi-retention, and now we have two sets of vectors. Okay, one from multi-retention, that is Z1, Z2, Z3. How we got it? We already seen that. And one original input, that is X1, X2, X3, which we have got through this residual connection or skip connection. The good thing is all these are 512 dimensions. These are already 512 and these are also 512 dimensions, which means you can perform any mathematical operation. And what operation we perform here? We perform addition. You see, that is nothing but this add. Okay, so we add Z1 plus X1, Z2 plus X2, Z3 plus X3. This gives us a new set of vectors, and that is nothing but Z1 dash, Z2 dash and Z3 dash. Now let me show you that particular part. You see everyone. After this, please understand, after this X1, X2, X3, right, after addition of X1, X2, X3 and Z1, Z2, Z3, right, after addition of this, we got Z1 dash, Z2 dash and Z3 dash. Now I am going to continue with this. Okay, now I am going to continue with this one. So we got Z1 dash, Z2 dash, Z3 dash, which are again 512 dimensions. All of them here, they are 512 dimensions. 512 dimensional vector, 512 dimensional vector. Okay. And finally everyone, we have to perform normalization. Something called as layer normalization is applied. You can see this. You can see this here in the original architecture. After doing addition, we are doing what? Normalization. So this norm means layer normalization everyone. Okay, that is what is basically shown here. In layer normalization, you take each vector like Z1 dash, Z2 dash and Z3 dash. Okay, so Z1 dash, which has 512 numbers, we calculate the mean of all these 512 numbers, calculate the standard deviation and normalize or standardize all 512 numbers within some given range. Okay, so we calculate the mean, that is mu, we calculate the standard deviation, that is sigma, and normalize or standardize all 512 numbers within given range. I hope if someone has basic idea about at least machine learning, they know how to normalize the data, how to standardize the data. Okay, so that is basically done here in layer normalization. It means what everyone? It means whenever I say normalize or standardize all 500 numbers, we try to bring them within some given range. You do the same work for Z2 dash and Z3 dash. After this operation, Z1 dash becomes Z1 normalized, Z2 dash becomes Z2 normalized and Z3 dash becomes Z3 normalized. You can see Z1 norm, Z2 norm, Z3 norm. By the way, why are we normalizing? The answer is simple. Just to stabilize the training process. I've told you, right? You must have come across normalization concept and standardization concept in machine learning as well. Okay? Just to stabilize the training process, we are normalizing. When you compute Z1, Z2, Z3 through multi-rate attention, right, as we have seen in the previous step, this Z1, Z2, Z3, Z1, Z2, Z3, when you compute all this through multi-head attention, this can be in any range. It means there is no upper or lower limit which is defined for this. And because you are multiplying two numbers and then doing another multiplication, there is no defined range for the self-attention output. This is not a good thing, right? Neural network training is generally stable when numbers are in small given range. So we need some mechanism to normalize these numbers into a small given range. That is what layer normalization is doing. Okay? This layer normalization is doing the same thing. It's trying to bring those values in some given range. Fine. I hope till this point, I hope so you are able to understand. Now, next is feed forward neural network. As you can see in the original architecture even, now we are here. Okay, we are here. We have seen multi-layer attention, add norm, and this residual connection. Now we are here. Okay, at this point. So next is what you can see, feed forward neural network. The feed forward neural network inside an encoder block is basically a 2-layer neural network. I'll show you that. It looks something like this. Okay, it's a 2-layer neural network. You can input 512 dimensional input to this neural network. Okay, 512 dimension input you can input to this particular neural network. The first layer has 2048 neurons. This layer has 2048 neurons. Each neuron has a ReLU activation function, rectified linear unit activation function. The second layer has 512 neurons, this one area, and it is having activation function which is linear. Now let us imagine that Z1 norm, Z2 norm, Z1 norm, Z2 norm and Z3 norm, let's say they form a matrix like this. Okay, a matrix like this, which is of 3 cross 512. It means what? It means 3 words, each word of 512 dimensions. You can think of this as sending a batch of data where the batch has 3 rows. First row, you see here, this is first row, this is second row and third row. But all 3 go simultaneously. This goes and multiplies with the weights. See here, all this go here and multiplies with these weights. How many weights are there? So as I have told you, this is 512 2048. So it will be like 512 cross 2048 weights. Right? That's why I have told you this goes and multiplies with the weights of the first layer, that is 512 cross 2048. Since both dimensions match, this is 512 cross 2048, and here everyone you see, right, this is basically 3 cross, this is basically 3 cross 512. This dimension and this dimension, they match, you see, right? So since both dimensions match, you can perform this multiplication, and what you get is a 3 cross 2048 dimensional matrix. You will get 3 cross 2048 dimensional matrix. That means 3 vectors, each of size 2048. Fine. Then you add the bias. Obviously 2048 neurons, that means there will be 2048 biases. Let's say I will just represent them with only one value, let's say B1. So B1 will be added. Okay, one for each neuron, one bias for each neuron, obviously. After that then you apply ReLU activation function. Why? As I told you, right, ReLU here. So why ReLU here? ReLU is for non-linearity. Okay, and once that is done, after this layer, the dimensionality increase from 512 to 2048. Now in the second layer here, you take this 3 cross 2048 matrix and multiply it with weights, that is these weights. These weights will be how many, everyone? As you can see, these are 2048 and 512. So everyone, these weights in the second layer, as you can see here in the second layer, you take this 3 cross 2048 and multiply it with weights. How many weights? 2048 cross this 512. So 2048 cross 512. Since these dimensions also match, you can do the multiplication. See, they match. So once you do the multiplication, everyone, what you get back is you get back 3 cross 5, 1, 2 matrix. That is 3 vectors, each of size 5, 1, 2. That is what you got here. Okay, and then you add bias. Let's say I'll call that bias. Obviously there will be biases. 512 neurons are there, so 512 biases will be there. So I will represent them as B2. So we add bias B2, let's say. Fine. So finally we got 3 cross 512 now. Obviously the question in your mind is, what is the benefit here? First we increase dimensionality to 2048. Then we reduce it back to 512. So what is the benefit of all these things? We end up with 3 cross 512 matrix again. So what was gained? The benefit is that we were able to introduce non-linearity. This is the motive of it. We were able to reduce non-linearity through rectified linear unit, ReLU activation function. The entire self-attention process is linear. Remember this. All operations are linear. But sometimes if you have data where there is some form of non-linear complexity, then you need a feed-forward neural network with non-linear activation to capture those non-linearities. And this feed-forward network is what introduces non-linearity into the model. I hope till this point you got the idea. Okay. After this, now again, interesting thing is we do the same thing again. We use residual connection. You see again this residual connection, right? In the original architecture, if I want to show it to you, so I am talking about this residual connection. You see, it is bypassing feed forward. You see this residual connection. So we use a residual connection bypassing the feed forward neural network and add output of feed forward neural network, whatever the output. So actually we are here now. Okay, here. So what happens, as I said, we do the same thing again. We use residual connection bypassing the feed forward neural network, okay, like this, and add the output of feed forward neural network with our input. And what was our input even? What was our input? As you can see, our input was Z1 norm, Z2 norm, Z3 norm. That's why you see this residual connection or cell skip connection. You see Y1, Y2, Y3 is what we have got as output of feed forward neural network, and we are adding it to the original input, the input which we got basically from layer normalization through this residual connection, Z1 norm, Z2 norm, Z3 norm. Okay, so our input was Z1 norm, Z2 norm, Z3 norm. We bypass this and bring it where the feed forward output is setting, and feed forward output is setting here, Y1, Y2, Y3. Okay, the feed forward output is Y1, Y2, Y3. These are also 512 dimensions each. This one also, this one also. We add them, that is Y1 plus Z1 norm, Y2 plus Z2 norm, Y3 plus Z3 norm. And this gives us, let's say, Y1 dash, Y2 dash, Y3 dash. Again, all are of 5, 1, 2 dimensions. And now everyone, we apply layer normalization again. You see here, layer normalization. That means in our original diagram, we are here, normalization. I am talking about this one even. After adding, I am talking about normalization. And this normalization is nothing but what? Layer normalization. Okay, I hope you understand that. So we apply layer normalization, getting Y1 normalized, Y2 normalized, and Y3 normalized. Okay, this is interesting. Y1 normalized, Y2 normalized, Y3 normalized will go to the next encoder block. You can see I written here, to the next encoder block. At the start only I have told you, right? How many encoder blocks are there? There are 6 encoder blocks. So the output, this output which we got here from the first encoder block, now will go to the next encoder block. That means everyone, as I've told you, we are done with this add and norm. in the first encoder block, and whatever the output which you got here, it will now go to the second encoder block. That means in our original architecture, we are here. But as I've told you, n value is 6, so like this 6 encoder blocks are there, right? So that means the output of first encoder block we got here, as I've told you we are here, this output will go as an input to the second encoder block, that is to the next encoder block. Just like x1, x2, x3, right? Whatever x1, x2, x3 was there initially, x1, x2, x3, right? Just like x1, x2, x3 were the input to the first encoder block. Similarly, this y1 norm, y2 norm, and y3 norm. Okay, y1 norm, y2 norm, y3 norm. This will become the input to the next encoder block. Okay, and then the same things repeat. Whatever we have seen till now, the same things repeat. There is also a multi-head attention block in the second encoder, everyone. Obviously, as I've told you, they are same, right? So there is also a multi-head attention block in the second encoder. Even though I have not drawn it, but I think you understand, right? It is exactly same, right? It is exactly same. I don't have enough space. That's why I did not draw every one of them, but you can imagine, right? Second encoder, whenever I say, it will be exactly same. So as I've told you, there is also a multi-head attention for second encoder block, right? We will do add and norm after multi-head attention in the second encoder block as well, like this. Then there is also a feed forward neural network in the second encoder block, and we will do add and norm in the second encoder block again after feed forward neural network. And we go like this to the next, that is third encoder block, and then to the next fourth encoder block, fifth encoder block, and then finally everyone to the sixth encoder block. Okay, one important thing you must remember, and don't get confused about this. Okay, although each encoder block has the same architecture, as I've told you, copy paste in terms of structure, the parameters are different for each block. This block, this block, this block, parameters are different. Whatever the weights and biases you have in multi-head attention of this block, that is first block, the weights and biases in the multi-head attention of another block, that is second block or third block, they are different. That is the meaning. So whatever the weights and biases which are in the feed forward neural network of one block, the weights and biases in the feed forward neural network of another block are different. Each encoder block has its own parameter values which keep changing during back propagation. Please remember this. Okay, fine. So whatever the output even which we got in the sixth encoder, this will go to the decoder. Okay, and that output obviously will be of 3 cross 512 dimension. Just to summarize all these things, all of you, just to summarize, let me show you. We start from our input example, right? We started from our input example. What was our input? As I've given you example here, even the input was this: I am Yogesh. In the input block, we do 3 operations: tokenization, embedding, and positional encoding. And from there we get vectors. Which one? X1, X2, X3. First encoder block, in that what we did, we applied multi-head attention in the first encoder block, right? As I've told you, 6 encoders are there. So in the first encoder block, you can see after the input will come across the multi-head attention as soon as it enters the first encoder block. That means what even here, right? X1, X2, X3 will go through multi-head attention, that is multiple self attentions. Then we have done add, residual, right? Add, residual, and then layer normalization. These operations we have done, adding to residual and layer normalization. That is nothing but this one. add and norm, and you see residual connection, skip connection. What are the meaning of this also we have discussed. Then what we did, we applied feed forward neural network. You see, we were here, now feed forward neural network, and then add residual and layer normalization again. That is nothing but you see here. Okay, feed forward neural network, right? And then what we have done is we have done addition and layer normalization again. Output becomes, the output of the first encoder block becomes the input to the second encoder block, and this repeats how many times? 6 times for all 6 encoder blocks, because we already discussed that there are 6 encoder blocks like this. And finally everyone, the output from the last encoder block goes to the decoder. That means in the original architecture, if I want to show you everyone, after 6 encoder, the output will come here, and this output will go here in the decoder. You see, in the decoder. Okay, a very important observation. See, this is all summary, whatever we have discussed till now. Okay, but a very important observation, whenever you look in this entire pipeline, if you take a sample at any point after input processing, you will always get a 3 cross 5 1 2 vector. This never changes everywhere, right? From here input processing everyone, you will always get 3 cross 5 1 2. When you leave this point, I told you, right, as a final output as well, you got what? 3 cross 5 1 2 vector. So when you leave this particular point, you get 3 cross 5 1 2. Like this, when you pass through last encoder block here like this, the output you get is 3 cross 5 1 2, and this is what you send to the decoder, as I've told you. So this is how the encoder part of transformer architecture works. We are focused on the encoder part of the transformer architecture. I hope so you are able to understand the working. If not, please go and please revise. Okay, in the next video everyone, we will discuss about the decoder part. I'll provide the link for the next video in the description itself. Okay, so that's it from my side. Thank you everyone. Thanks a lot.